Hello, welcome to this video. Today we're going to do this problem. So this is a functional equation, classic one. We need to find all functions f from the real numbers. So the real numbers that satisfy for all real numbers x and y, this equation. F of x f of y plus y is equal to y f of x plus f of y. So first of all, before tackling this, I'm going to prove like a side theorem, which is going to involve another side, a side theorem. So first thing we're going to prove is that if f of x plus f of y is equal to f of x plus y, and f is monotonically increasing, meaning that y is greater or equal than x, means that f of y is greater than or equal than f of x. If these are true, then f of x equals cx for some non-negative real number c. So let's prove this claim. So first of all, let's ignore the monotonically increasing bit. Let's focus on this equation. Let's notice that if I have f of say x plus f of 1, it's going to be f of x plus 1. And so, if I replace x with a positive integer n, that means that f of x, f of n plus 1, minus f of n, so I move this f of x to the other side, is f of 1. But now, I can look at f of n as f of 1 plus the sum. This k goes from 1 to n minus 1 of f of k plus 1 minus f of k, right? Because this is the telescoping series. We're going to have f of n minus f of n minus 1 plus f of n minus 1 minus f of n minus 2 plus f of n minus 2 minus f of n minus 3, and so on. And all these brittle terms will cancel out, and we'll get f of n minus f of 1, and f of 1 will cancel. So this we know is just constant f of 1, and summing over a constant is just that constant times the amount of terms here. So we have n minus 1 terms here, so we get f of 1 plus n minus 1 times f of 1, which is n times f of 1. So we found that f of n is equal to n times f of 1 for any n that's bigger than or equal than 1 and an integer. And notice, actually I should have done this earlier, if I plug in x is equal to y is equal to 0, we get f of 0 plus f of 0 equals f of 0, right? 0 plus 0 is 0. So this cancels out and we get f of 0 equals 0. And if I plug in y equals to negative x, I get f of negative x plus f of x is equal to f of 0, which is 0. Which means that by its definition, f is an odd function. So f is an odd function, meaning that I can say for n smaller or equal than negative 1, that are whole numbers, f of n is equal to negative f of negative n. Now this is an integer that's at least 1. That's at least 1, so we know this is negative n times f of 1. And so this is n times f of 1. So in general, for any whole number n, f of n is n times a constant f of 1. Now let's notice, what if I, instead of doing 1, did more generally to any x? So if I say, now, f of x plus f of x is f of x plus x, which is f of 2x, and this is 2f of x. And then I can add another x, so 3f of x is f of x plus f of 2x, which is f of x plus 2x, which is f of 3x. And again, in general, you can prove this easily by induction. Get f of nx is equal to nf of x. And now, so this is true for any positive integer n. So now, if I replace x, so if I substitute x as a rational number with the denominator of n, I get nf of m over n is equal to f of m over n times n, which is m. We know this is m of times f of 1. And I should say m is an integer while n is a positive integer. Which means that the fraction m over n is some general rational number. So from this we get f of m over n is equal to m over n times f of 1. Which means that we got that f, if we name f of 1 as a constant c, we have that this is c times m over n. So it's linear, but for rational numbers. Now let's use this. So let's have some general not rational but real number r. We know that the rational numbers are, I believe it's called a dense set inside the set of R, which means that there are inside the set R, for any number R inside, there is a series of rational numbers, so Q1, Q2, so forth. So a general series Qn, where Qn is a rational number, such that the limit of Qn approaches R. So if this is true, I might do a video on this, but I'm gonna say something that's a little bit different. It can also be easily proven. I'm saying that for any number R, there are two series of rational numbers, one that's approaching that number from below, and one that's approaching it from above. So by that I mean there is a series of numbers such that Q1 is smaller than Q2, smaller than Q3, and so on. All of these are rational numbers such that Qn approaches R. And there's also a series that approaches it from below, because it's like increasing towards the number R. And there is a decreasing series. P1 is greater than or equal to P2, P3, and so on. Also a series of rational numbers, such that Pn also approaches R. These two are true. This statement is also true. It's also pretty easy. With a little bit of thinking, you can also prove this. But nonetheless, we're going to use it. So given our number R, we know these two series exist. But now we can say, well, since it's approaching R, since Q1 is approaching R from below, and Pn is approaching it from above, we always have this inequality. Right? But we know since f is monotonic, we can put an f on each one of these. So f of Qn smaller than or equal than f of R smaller than or equal than f of Pn. But we know this is C times Qn, and this is C times Pn, right? So this series approaches R times C, and this series also approaches R times C, right? So we have a series. This is like a constant series. So this series is C times Q1, C times Q2, and so on. This is C times P1, C times P2, and so on. This series is just f of R and f of R and so on. So this is a series bounded by two other series that are approaching the same limit. So we know that by the sandwich theorem, this series also approaches the same limit. But a constant series obviously approaches that constant. If you have a series that is just a constant number, say 5, so 5, 5, 5, 5, and so on, its limit is 5. So this limit is, we know, has to also equal f of R, which means that for any real number R, f of R is equal to R times some constant C. That constant C is f of 1. And just finish off, C is bigger than or equal to 0, because we know that is bigger than or equal than 0, so f of 1, which is C, is bigger than or equal than f of 0, which is 0. So we found that from these two, we can get, after all this mess, that f of R is equal to R times C for any real number R, and a constant C that is at least 0. So we proved what we wanted to. So now let's erase the board and prove the next statement. Okay, so let's prove this second statement. So this statement says if we have this original condition, so f of x plus f of y is equal to f of x plus y, and another condition, this time f of x times f of y is equal to f of x times y, then that means that either for all x, f of x is equal to x, so f is the identity function, or for all x, f of x is equal to 0, aka f is the 0 function. So let's prove this. So first of all, let's explore this extra condition. Let's plug in x and let's plug in y is equal to x. So we get from this f of x times f of x is equal to f of x squared is equal to f of x all squared. That's interesting. Now, if let's say I have some number x0 which is at least 0, that means that f of x0 is equal to f of square root x0 squared, which means that it is at least 0. So for any non-negative number, f outputs another non-negative number. So now, let's see. So now let's say we have y bigger than or equal than x. That means that f of y is equal to f of x plus y minus x, which is equal to f of x plus f of y minus x. We know y is bigger than or equal than x, which means y minus x is at least 0. So from this claim, we know that this entire thing is bigger than or equal than 0, which means that adding f of x means that it's bigger than or equal than f of x. Which means that if y is bigger than or equal than x, then f of y is bigger than or equal than f of x. which is exactly this condition. And we already know that if a function is monotonically increasing and is additive, so that's what this means, f of x plus f of y is equal to f of x plus y means that it's additive. If both of these are true, we found out that f is linear, it's a constant times x, which means f of x is a constant times x. Now let's plug it into this equation to find this constant. So we get c times x times c times y is equal to c times xy. So if x and y are non-negative, which we can choose them to be, say x and y are both 1, doesn't matter, can cancel them out, and we get c squared is equal to c, so z is 0 or 1, which means that either for any value of x, f of x is equal to x, or for any value of x, f of x is 0 times x, which is 0, which is exactly what we wanted. So f is either the identity or the 0 function. So we proved the second statement. Now let's again clear the board and finally tackle this, the original question. Alright, let's do this. Let's finally do this question. So first of all, a good idea when you're tackling any equation, any functional equation, is to try to plug in values like x is equal to 0 or x is equal to y or y is equal to 0 to find some values, because usually f of 0 is very useful to have as a value. So let's plug in x is equal to 0. So x is equal to 0 gives us x f of y 0, so plus y is just y. So we have f of y is equal to y f of 0 plus f of y. Notice y cancels out, so we'll get that y f of 0 is equal to 0 for any value y. So I can pick some non-zero value for y, like 1 or pi, doesn't matter. We get f of 0 equals 0. That's nice. Okay. Okay, now another useful thing to do, usually in most functional equations you get f of 0 equals 0. Another thing that's usually useful is proving that if a function is 0, if a function's output is 0, then its input was originally 0. So basically we want to prove that if f of x is equal to 0, then x is equal to 0. That's what we're looking for. This sometimes will not be true, but this time we'll see that it is. So let's prove this. And actually, this is not completely true. First of all, before we do this, we have to assume something. So first of all, notice that the function is 0. So if f of x is equal to 0, that works. Because this will be 0, 0, 0. 0 is 0 plus 0. That's correct. So this is immediately a solution. So now this is the case where f of x is not 0 for all x. Okay, so there exists some value x such that f of x is not 0. That's the case we're looking for. So now let's prove this. So if this is true, let's plug in y as that value x. So let's call it x0, so just we don't get confused. So let's set y to be x0, x f of y will be 0, and we'll get f of x0 plus, that's it, it's just equal to x f of x0 f of x plus f of x0. So we can say both of these are the 0, or they just cancel out. we get that x0, f of x, is 0. And this is true for any x. Which means if I can find a value of x such that f of x is not 0, then that means x0 is equal to 0. But that's exactly my case. I'm assuming there exists an x such that f of x is not 0. So if I plug in that specific x in here, we'll get that f of x cancels out. We'll get x0 is equal to 0. Okay, that's good. Now, so now let's try to make this side of the equation 0. Because now we'll know whatever is inside this f will also have to be 0. So the way I see to do that is make this y -1, so that we get f of something minus f of something, and we want that to be 0. So let's make the things inside the f equal. So I'm searching for y is equal to -1, and also x is equal to 1. So we'll look at the case, x is equal to y, is equal to -1. But we get f of -1 minus 1 is equal to negative f of -1 plus f of -1. And exactly how we want it to, this cancels out and we get 0. But we know if f of anything is 0, then that thing is 0. Which means that negative f of -1 minus 1 is 0. Which means that f of -1 is -1. Right, I move f of -1 to the other side. So this is true. Now, let's just plug in y is equal to -1, because I'm seeing a lot of f of y, and just y, and I know they're both going to be -1, and it's going to turn out as a nice equation. So, if we substitute in y is equal to -1, we get f of -1 is -1, so times x we get -x, then minus 1, that's negative f of x, minus 1. Okay, that's useful. So that means if I have the value of the function at some value x, then I have the function's value at -x minus 1. And we have it from this equation, but let's look at it a little differently. What if x was equal to -x minus 1? Then we'll be able to move to the other side, divide by 2, and get its -1/2. But there is a value, an exact one value, that x is equal to -x minus 1. We can just move x to the other side and divide by 2. X is -1/2. So if I substitute in x is -1/2 to this equation, we get f of -1/2 is equal to f of -1/2 minus 1. And like I said earlier, move this to the other side and divide by 2. We get f of -1/2 is equal to -1/2. Okay, that's also nice. Now, let's plug in here x is equal to 1. So when you plug into the original x is equal to 1, we get f of y plus y is equal to y f of 1 plus f of y. Okay, so if we find the value of y such that we know what f of y plus y is and what f of y is, then we'll be able to find f of 1. And other than 0, of course, because then we'll get 0 equals 0 plus 0. But let's look at -1/2. We'll get -1/2. -1/2 is -1. We know it's f of -1. It's -1. And we know what f of -1/2 is -1/2. So if I plug in y is equal to -1/2, I get f of -1/2, like we said, -1/2 minus 1/2 is equal to -1/2 f of 1, f of -1/2 is -1/2. So this is true. This f negative a half minus a half is f of negative 1, which like we said is negative 1. We can move a plus 1 half to the other side. Negative 1 half times f of 1 is equal to a negative 1 plus 1 half. It's negative a half. Divide by 2 and multiply by negative 1. F of 1 is equal to 1. That's very important. Because now, let's see. Now if I plug into here y is equal to 1, I get that I know what f of 1 is. F of 1 is 1. So this will get me f of x plus 1 is equal to f of x plus f of 1, which again is 1. Okay, that already looks very promising. That means that if I have a value of the function and I step up by 1, then the function is also going to step up by 1. That's useful. And now, when you get to this sort of equation, a common trick and a very useful one, usually, will be to substitute in here either replace x with x plus 1 or replace y with y plus 1. Because then you'll be able to substitute back in things from the original equation and get things that are more general than this. So let's use it here. Let's replace x with x plus 1 and see how that helps us. So we have f of replace x with x plus 1. So this stays the same, but we have an extra f of y inside here. So that's f of x f of y plus 1 plus that extra f of y is equal to now f of x plus 1 is f of x plus 1, which means that after replacing x with x plus 1, this thing here is going to get me an extra y at the end. This is y f of x plus f of y plus that extra y. Okay, that looks nice. Now, we know what this thing is. It's f of this, f of x f of y plus y. So this thing here is f of x f of y plus y. Okay, so the function already looks sort of additive. Now let's make it even closer to that. Let's notice that for y that's not 0, we know that f of y is not 0 from this, because if f of y were 0, then y would be 0, which is a contradiction. So f of y is not 0, which means that I can take x. It's going to look like a very arbitrary decision, but you'll soon see why I said this. Some value z, general value z, minus y divided by f of y, which we know is not 0, so the denominator is non-zero, so this is legal to do. If I place this back to the equation, notice that x f of y plus y will be exactly that arbitrary value that I picked as z. So from this I get f of this thing is z plus f of y is equal to f of z plus y. So it's almost additive. If you would have replaced y with f of y, this thing would be additive. Now this is for y is not 0, but notice that this is obvious for y that is 0 too, because f of 0 is 0, we get f of z is equal to f of z plus 0, so f of z is equal to f of z, that's obviously true. So this is actually true for any y you plug in here. But now let's plug in here a value of z instead. If I plug into here z equals 0, I get f of y is equal to just f of 0, 0, we get y. Which means, so after I do the function over itself, so I get back to where I started. or in other words, the function is equal to its inverse. That's very cool. Now if I replace here y with f of y, then I'm gonna have here f of y, which is y, here just f of y. Let's do that up here so it's more visible. We get f of z plus f of y. Yes. Equal to f of z plus f of y. And we know this value is y. So f of z plus y is equal to f of z plus f of y. So our function f is additive. That's very nice. Because now that this is true, I can use this on the original equation and take this plus y out as a plus f of y on the outside. So let's do it. It's down here. So we have f of x f of y plus y is equal to f of x f of y plus f of y. And we know that's from the original equation equal to y f of x plus f of y. We can cancel out f of y and get that f of x of y is equal to y of x. Okay? Now this is very close to the function being multiplicative. If we would have swapped y and f of y, then that would have been exactly said that the function is multiplicative. We can use the same trick we used here, or from here to here, replacing y with f of y, and we know f of y is y, so that basically just swaps the two in any equation you want. So if we use this again, this f of y will turn to y, this y will turn to f of y, and we'll get f of xy is equal to f of x times f of y. And just again to be clear, we got from this by replacing y with f of y. So this y turned to this f of y, this f of y turned to f of y, which we know is y, and so this is this y. Okay, but now we got the function is additive, and then the function is multiplicative, which means that we can use this thing we proved. And we know that the function, we're assuming that the function is not the zero function, which means that this option is out the way. So the only thing that this function can be is the identity function. So the second option, where f of x is equal to 0, is it can only be f of x is equal to x. And you can also check that this function really works. So f of y turns to y, x y plus y, f of that thing is itself, so that's x times y plus y. And here similarly, this is x times y plus this is y. So the equation is true. So the final solution for this functional equation is either the zero function or the identity function. And just one last final thing. When you're solving functional equations, this claim definitely, and also usually this claim, are claims that you can use without proving. You can immediately say, this is true, okay, f of x is linear, or this is true, it's the identity or the zero function. You don't have, if you're like in an Olympiad or something, you don't have to reprove that each time, as far as I know. I just proved it to make it clear that I'm not just making it up, and really making it more clear why these are true and how we got from multiplicative and linear to boom, it's the identity. That was the entire question. And finally, that's it. If you want more content like this, please subscribe to my channel. I'll be uploading more interesting problems and things like this in the future. And finally, that's it.